Hi everyone, welcome to 2.6 Combined Transformations. Today we're going to add on from what we learned in 2.4 and 2.5, and we're going to take a look at doing multiple transformations within the same questions. So specifically, you're going to see a bunch of examples in which we reflect, expand, compress, and translate our functions. Now, in terms of creating an order of operations, we're going to use the acronym RECT to help us out with that. So that's going to say we'll do reflections first, then expansions, compressions, and then translations. So in the same way that when you do algebra, you use BEDMAS for your order of operations, we're going to say that we're going to use RECT here for graphing our transformations. Now, there's multiple ways to be able to graph transformations, and a really common alternative way is to be able to create some sort of formula where you create a point that has certain variables that you'll be able to sub in some values for to be able to quickly find what your final points are. And that may be a little bit more efficient from time to time. We're going to take you through the step-by-step process here of graphing each step of the transformation. And one real advantage of that is it's going to help you see what's happening with the transformation. And another advantage is it shows your work along the way. So in the same way that when you do an algebraic process, you can get rewarded for part of the process, even if the final solution isn't correct. The same thing can happen with these transformations questions. If you do part of it correct, you'll be rewarded for the process. Now, if there's anything in terms of an absolute value function, inverse function, reciprocal function, anything else, you want to be able to do that operation first before you perform your rect. So take a look at the first example here. We have y equals -2 f of x minus 3 plus 1, and that's being transformed from our f of x function that you can see below here. Now, we'll highlight some of the key points. And those are the points that we're going to end up transforming here. On the side, especially for the first couple times that you do this, you want to be able to list what your steps are for your transformations. Look and see if there's any negatives in front of your function, in front of the x, and we notice that there is a negative right here, and it's in front of our entire function. It's to the left of the f, and so that means that we're going to have a reflection over the x-axis. The 2 is telling us that our function, our f of x function, is doubling its output values. So we're going to have a vertical expansion by a factor of 2, and then we're going to move 3 units to the right and 1 unit up. Okay. If you want to try this out on your own, you may want to pause the video right here and see if you could perform each of those operations and come up with your final new function. Otherwise, you can follow along here and we'll do this step by step. So to reflect over the x-axis, we have a mirror image. So if you have a y value of 4, we're going to flip it and create a y value of -4. And we're going to do that to each of these points right here. And depending on how you want to do this, you may want to do something where you can join them like that. And that shows our reflection over the x-axis. An advantage is if you do have multiple colors available, you might want to get some different colors to be able to show what's going to happen for each of the steps. So for instance, for a vertical expansion by a factor of 2, I'm going to use red here. And I'm going to take each of those key points again that we did, and now I'm going to double the y values. So a y value of -4 gets doubled and becomes a y value of -8. And each of our y values are doubled. And when you join that, that's going to create something here that's going to look like it's been stretched twice as much. And then finally, you want to translate it 3 units to the right and 1 unit up. So we'll take a different color here again, and we'll go 3 units to the right, 1, 2, 3, up 1. And this final graph right here, we want to make sure that everybody knows that that's our final graph. So we're going to write final right there. And that is what we want. So when you're taking a look at this and you're figuring out how am I going to be assessed on it, if you graph nothing but the final graph and you didn't do the steps along the way, and that's correct, you'll get full marks for that. But sometimes it's nice to be able to see the step-by-step process of what we have right there. Okay, we'll look at a couple more examples and we'll see what we can do with each of these. Now, one thing you're going to hear me talk about a lot today is something called ready form. And that's just saying if our transformations aren't in ready form. So for instance, if we need to do some algebra to get y isolated, or in this case, if we have a 1/2 right here, we need to make sure that we factor that out so that it represents what is really happening within the bracket right there. So right now there's that 1/2 in front of the x, and we need to take that out to put it into ready form. And when we factor out the 1/2, it still stays to the right of the f. Nothing's happening where it would affect any sort of values to the left of the f. It's not going to have anything to do with our vertical expansions or compressions. But what we could say is something like this. It's going to become y equals f of, we'll factor out a 1/2, and then when you factor out a 1/2 from there, you're thinking I'm dividing a 1/2 from 2, and 4 halves go into 2, so this becomes x plus 4. And you can do a quick check. You could have tried to multiply that back in just to confirm that, yes, that is what the expansion would look like. So this 1/2 still is acting on the x values. But what it's telling us now is instead of what may have looked like a translation of 2 units to the left, this is a translation of 4 units to the left. So make sure that you've factored it to get it into ready form. So if we label what's going on, we have a vertical compression by a factor of 1/2, and we're going to go 4 units to the left and 1 unit down. Now, this question in particular is going to be a little bit frustrating to do the method that we do because we're going to be going literally off the charts on this one. If you take a look at this, we have a vertical compression. Oh, you know what? I made a mistake right here. That vertical compression, that 1/2 there is a vertical, that is a horizontal expansion by a factor of 2. I'm sorry for confusing you, and if that did look kind of strange, hopefully you're able to see that we did make an adjustment with that right there. Okay, so the horizontal expansion by a factor of 2. Boom, boom. So that means that we're going to take each of our x values and we are going to double them. And we're going to double them. Okay, and that's going to be a little bit frustrating because now we're off the charts on this. If we join this right here, we have a graph that looks like that. It's been horizontally expanded by a factor of 2. And then let's see what we could do here by going 4 left and 1 down. Okay, and you're going to get a final graph that's going to look like that. So once again, let me just talk about this once here because I said this incorrectly the first time. If you had a value in front of your f, to the left of the f, that would be some sort of vertical expansion or compression. Because this is next to the x, this is a horizontal expansion or compression, and we know that something like that, y equals f of 1/2 x, that is for sure a horizontal expansion by a factor of 2, just like we have right there. If you had something like y equals f of 2x, then now we know that would be something that would be a horizontal compression by a factor of 1/2. Okay, example 3. We have to put this in ready form. So we're going to divide everything by -2 to isolate for our y. And when we divide this by -2, we're dividing two pieces on this right side by -2. So if we were to rewrite this, it would be y equals, instead of saying divided by -2, you could have something that says -1/2 f of x plus 1 minus, whoops, that's not going to be a 4. That's going to be -4 divided by -2. That's going to be a positive 2 right there. Okay, so that -2 acted on the f of x plus 1 and on the -4. Let's label what's going on. We have 1, 2, 3 things. There's a negative in front of our function, so that means that we're going to be reflecting over the x-axis. The 1/2 tells us that we have a vertical compression by a factor of 1/2, and then we're going to go 1 left and 2 up. So let's highlight some of our key points again right here. So we reflect over the x-axis. Okay, and then after that, we want to vertically compress it by a factor of 1/2. So you may have half points here, like we do in this case. So each of those y values become half of what they were before. And then we want to go 1 left and 2 up for our final. And you're going to get that right there. Okay. Now we could take a look in example 4 of having some translations in which now we need to express this algebraically, and we're going to do that with the function y equals x squared plus 2x. Okay, now note it says simplifying is not necessary here, and you'll see why that happens when we change everything in this example. So if we want to compress something horizontally by a factor of 1/2, we know that that means that if you had something where you had an x value, so say for instance we had something like y equals f of x, and you were to compress it horizontally by a factor of 1/2, we know that that becomes f of 2x. So where you used to have an x, you now have a 2x. And then after that, we're going to translate that 6 units to the right. So in other words, our x is now going to be times by 2, and then after that, on top of that, we're going to translate it 6 units to the right. So whatever our original x value is, it's now going to be replaced with a bracketed 2x minus 6. So take a look at what that would look like now when we take the function y equals x squared plus 2x. Wherever there's an x, we're going to replace it with 2x minus 6. So we would have y equals bracket and it'll look like that. So wherever there was an x, we've replaced it, and it may make more sense now that we don't need to simplify it from here. This is your best final answer. By expanding and simplifying, you would actually make it look a little more complicated. It'd be tough to be able to figure out what the actual transformation was. So by leaving it in this form, it's telling us that we have a horizontal compression by 1/2, and then we're moving it 6 units to the right. And then finally here it says horizontally expand this by a factor of 3. So that's going back to this original question right here, and then reflect it over the y-axis. So if you had something in which you're horizontally expanding by a factor of 3, your x would be replaced with a 1/3 x. And then if we're going to reflect that over the y-axis, that means that our x values become the opposite. They're going to become times by a negative sign. And so what we can do there is we could say that would be the same as putting a negative in front of here, because it'll act on that x right there. And so wherever you have an x, you're now going to replace that with a negative 1/3 x. So if we write out our function, we would say y equals, and instead of having x squared, we're going to say we have negative 1/3 x squared plus 2 negative 1/3 x. Okay, and once again, that's our best final answer for that question. Okay, here we're being asked our original function. Hopefully you guys can see that your original function is this one on top right here. That's given in gray, and it's saying what would be the transformed function below. So what you could do with something like that is you know that it's being reflected, and I would recommend going in the rect order again. And so if you have something like that, we can actually do the question, and we'll say if we're reflecting it over the x-axis, you would create something that would look like that. And let's just make a note that we did that. We reflected it over the x-axis. The distance from point to point is 1, 2, 3, 4 units. And if you notice on the new graph, that's going to be a distance of 1, 2, 3, 4, 5, 6, 7, 8 units. So we are doubling our horizontal value, which means we have a horizontal expansion by a factor of 2. And if you perform that operation on our graph right here, and you take this point and this point and this point, and we horizontally expand that by a factor of 2 and double our x values, you would get something that would look like that. And it is almost the same as what our final function is supposed to look like, except we need to move everything 1 unit to the left. And so if we move everything from there 1 unit to the left, we would have our final function. So it's asking for the equation of this transformed function right here. So let's see if we can put this all together now. Once again, if you're doing this video, I would pause it right now and see if you could write what you think your final solution would be. Okay, and you can check your solution and see how that looks. The negative in front of here is representing that we're reflecting it over the x-axis. We have a horizontal expansion. It's connected to the x right there. So it's to the right of the f. So that's a horizontal expansion by a factor of 2. And then we're moving 1 unit to the left. So all 3 of those seem to check out. And if you did your rect, then you should be correct. Okay, here's a good test to see how we're doing right now. Given these functions, we have a square root function, we have a quadratic function, we have an absolute value function, and we have a reciprocal function. And they're saying, can you now provide some transformations to see what would happen with each of these? In 2.4, 2.5, we began our first part of the lesson by graphing some basic functions. So what I would recommend right here is let's see what our basic functions look like, and then let's make sure we're in ready form and we can apply the proper transformations. So really quickly right now, I'm going to graph a basic square root function, quadratic function, absolute value function, and a reciprocal. So let's do that right now, and then we'll give you a chance to be able to look at them in a little bit more detail. Okay, the reciprocal function we might need a little bit of a review on. So if we're saying this was y equals the square root of x, this is y equals x squared, this is y equals the absolute value of x, this is going to be y equals 1 over x. Okay, so what I would do right now is I would pause the video and let's see if we're able to come up with our final solutions for this. So take a few minutes right now, work on these examples, and see if you can produce the same final solutions. So let's take a look. So if we want to isolate for y here, we need to times both sides by 2. And we know that 2 gets distributed. So we would have something that say y equals negative 2 root x minus 1 plus 4. Okay, so the negative here tells us that we're going to reflect it over the x-axis. We're going to vertically expand it by a factor of 2. And then we're going to go 1 to the right and 4 up for our final solution right here. Okay. And there's our square root function right there. For our quadratic function right here, we have a vertical expansion by a factor of 3 over 2. and we're moving 1 to the left and then 5 down. So vertical expansion by a factor of 3 over 2. So it's going to be a little bit tougher than some of our past graphs. So you're going to times your y values by 1.5. Oops. So a 4, for instance, is going to become a 6. And let's graph that right there first. Okay, so that's our vertical expansion by a factor of 3 over 2. And let's go 1 to the left and down 5. Okay, and that's going to be our final solution right there. So let's make sure we label our final solution there, just like this guy right here. That was our final solution there. Okay, so we treat these brackets right here. That would just be similar to how we treated our brackets for some previous questions. So this 2 is to the left of the bracket, meaning that that is going to be a vertical expansion by a factor of 2. And then we're going 3 units to the right. So vertical expansion by a factor of 2, we can double our y values. And then after that, we want to move everything 3 to the right. Okay, and that's going to be our final solution right there. Okay, and then our reciprocal function, we actually only have one transformation happening. We're just moving everything 3 to the left. And so if you have your original graph right here, and I mean, this is definitely a sketch, if anything else, we're going to shift everything 3 to the left. So that includes shifting the asymptote 3 to the left. Okay, and then we'll shift this point here, 1, 2, 3, 1, 2. Okay, and that's going to be our final graph right there. Okay, so that's transforming some more specific functions. We have one final example right here, and this is good in terms of working on our order of operations. So here we have an absolute value happening to our function. So when you have absolute value, you want to do that function, that transformation first. So as you'll remember, absolute value means anything that's below the x-axis is going to be reflected above the x-axis. So for this first example right here, if you're to list your different steps, we would say, number 1, we have to take its absolute value, and then we're going to vertically expand it by a factor of 2, and then we're going to go 1 unit down. We take some of our key points right here, and if we vertically expand that by a factor of 2, sorry, if we take its absolute value, we'll go 1, 2, 3, 1, 2, 3 right here. We're gonna get something that looks like that, and any points that are already above the x-axis, they just stay above the x-axis. So that's our first transformation. Then we need to vertically expand it by a factor of 2. And then finally, they want us to move it down 1 unit. So here we go down 1 unit, down 1 unit. So common question that people ask is, can you go below the x-axis on an absolute value transformation? And the answer is yes, because some of the other transformations are going to ask for you to do that. And so we've done everything in the correct order, and that's our final answer right there. Okay, so this last example, we have an absolute value function happening, but we also have that subtract 3 happening within the absolute value. So this is definitely one of the more tricky concepts. We're taking its absolute value, but in the same way that when you have brackets, you do whatever's within the brackets first. When you have an absolute value occurring to your function, you have to do whatever's within that absolute value first. So if this is saying f of x subtract 3, that would mean that on its own, y equals f of x subtract 3, we're going down 3. And we need to go down 3. And once that's gone down 3, that's the function that we're taking the absolute value of. So your order of operations is really, really tricky here. Treat those absolute value bars like brackets. If there's something happening within the absolute value bars, you have to perform that transformation first, and that's why we're going down 3 first, because that's inside. Okay, if you want to see a counter example, if you had something like y equals the absolute value of f of x subtract 3, this would mean that you would first take its absolute value, and then you could go 3 down after that. That's not the example we're looking at, so we will pause that right there, and let's go down 3. Okay, and then after that, we want to take its absolute value, so we'll get a different color right here. We'll go 1, 2, 3, 1. So anything that's below the x-axis is going to become a mirror image above the x-axis. Okay, and that will be our final solution. Okay, that's it for today. You have a chance to be able to work on your homework. We'll talk about the chapter review, but you have a chance to be able to get started on your homework right there. Thanks for listening.